Yeah. So let us welcome in lecture number 8, 9 in the lecture series of real numbers, real analysis 1. So in last lecture, we proved, we solved three examples. So example number 3 was, if P is infinite set, subset of countable set A, then prove that P is countable. That is, infinite subset of countable set is countable. So let's take suppose A is countable set and B is any infinite subset of A. So naturally, our claims that B is countable. So since B is subset of A, then each element of B will be in A and naturally it will be AI, because all elements of A, capital A are A1, A2 means in AIs. So let us take suppose small n1 with the smallest subscript for which an1 is element of B. So next smallest subscript we are taking suppose small n2. So for which a into will be element of B, and here we are getting small n1 which is less than n2. So we are taking small n1 which is the smallest among all. Small n2 is the next smallest, and n3 will be next smallest, means it is greater than small n1 and n2. So you'll get C. So if we continue this process, so you'll get all elements of B, capital B, an1, an2, an3, and likewise, means you are getting counting scheme for elements of B, means all elements you are giving to all elements of B you are giving leveling, and therefore capital B will be countable set. So that was the example number 3. So what is example number 4? Example number 4 is that prove that the set of rational numbers in close interval 0 1 is countable. Already we proved one example, that is example number 1 2, that is set of all rational numbers is already countable set, and this set of all rational numbers between 0 and 1, naturally it will be infinite subset of set of all rational numbers. So using previous example, that is every infinite subset of countable set is countable. So we get the set of all rational numbers in the close interval 0 1 is countable. So example number 5. See, what is example number 5? Show that if capital A and capital B are countable sets, then Cartesian product of A cross B, Cartesian product of A and B, that is A cross B, is also countable. That is very true. So naturally we are taking capital A and B are countable sets. So there exists counting schemes to both sets A and B. Suppose capital A is A1, A2, A3 and goes to infinity, and capital B, it is suppose B1, B2, B3, B4 and goes to infinity. So naturally A and B are countable sets. What is our claim? Our claim is that capital A cross B is countable set. That is very true. So for that, see, so here we are letting capital AN. See, what is capital AN? Capital AN, it is cross product of two sets. See, capital A cross singleton BN. What is singleton BN? It is nth element of capital B. See, so similarly, so what will be A1? If we see, if we use the definition of capital AN, so you'll get capital A1, capital A cross B1. Similarly, what is capital A2? Capital A cross singleton B2. And in similar way, you'll get A3, capital A4, and what is capital A? It is cross product of capital A with singleton set Bn, that is nth element of B. So if we list all element of capital An, so you'll get counting scheme for An, and it is true for each n varies from 1 to 3. So it means that capital An is countable set for each n, means capital A1 is countable, capital A2 is countable, capital A3 is countable, capital N is countable, capital N plus 1 is countable, and so on. It means that each set in this union is countable, and this is countable union of countable sets. So naturally this union will be countable using previous theorem, and you'll get A cross B equal to this union, and therefore A cross B will be countable set. So that is solution of problem number 5. What is problem number 6? Show that If capital B is countable subset of uncountable set A. So B is countable, capital A is uncountable, and B is subset of A. See, then what we have to prove? Capital A minus B is uncountable. So if you just draw just random figure, I'm not drawing exact figure for this problem, but it is random. See. So on the contrary, I assume that suppose capital A minus B is countable. So what we have to prove? A minus B is uncountable. So on the contrary, we are assuming that A minus B is uncountable. So if A minus B is uncountable, but already you can write A as A minus B union B, and you have given capital B is countable. So capital B is countable set. It is given. C, and A minus B is countable. That is our assumption. C. So A minus B is also countable. So it is our assumption. It means that you write capital A as union of countable union countable. Means countable union countable is again countable. So it directly gives that A is countable. But see what is hypothesis of this problem? See, in hypothesis we have given that capital A is uncountable set. You cannot change hypothesis. So let us see. So A is uncountable set, and here I am getting A is countable, which is contradiction to our C hypothesis. Hence, we get this contradiction because of our assumption. And what was the assumption? See, our assumption was A is uncountable. See, sorry. What was our assumption? A minus B is uncountable. So we assume A minus B is countable. Hence, naturally A minus B should be uncountable. That is solution of this problem. So in next means this lecture, that is lecture number 9. So first we will define, see what is real number. So our next topic, that is the real numbers. See, what is the definition of real number? See, already we know all these things. We know that every real number small x can be written in the form, in decimal expansion form. In decimal expansion as, see, always you write, suppose x is real number, it may be 1.23 something. See, so always any real number you can write in decimal expansion as, suppose b point, I'm writing a1, a2, a3, it goes to infinity. And how will write this decimal expansion? See, I will write it as b plus a1 divided by 10 plus a2 divided by 10 square means 100 plus a3 divided by 10 cube, and you can continue this. Every real number always write in the decimal expansion. See, so this will be resulting form of this decimal expansion of real number. You can observe, for example, see, so what is the decimal expansion of, see, decimal expansion of, suppose I'm writing 3.75893 or 5 6. So how we write this number is, so write 3.758956 as, see, so it will be 3 plus 7 divided by 10 plus 5 divided by 10 square plus 8 divided by 10 cube plus 9 divided by 10 raised to 4 plus 5 divided by 10 raised to 5 plus 6 divided by 10 raised to 6 and plus what is next? So next digit is 0, so that will be 0 divided by something, 0 divided by 10 raised to 7 and it will be 0. See, so remaining terms will be 0. So this is decimal expansion of 3.758956. So you can observe. So what is that? What is the value of 7 point? If you write this, it will be 3 plus. What is 7 divided by 10? It is 0.7 plus. What is 5 divided by 10 square? It is 0.05 plus. What is 8 divided by 10 cube? So it is 0.008 plus. What is 9 divided by 10 raised to 4? It is 0.90009. Yeah, sorry. It will be 0.0009 plus what is next? It will be 0.00005 plus it will be 0.00005 times and that is 6. So if you add these terms, these numbers, so you'll get this number. So this is decimal expansion of 3.758956. Means every real number x always can be written in its decimal expansion in this way. See, so this is equivalent form of x. It is called decimal expansion. See, so next there is theorem. Actually, here what is this a1, a2, a3? So here you can write a1, a2, and so on. So these are less than equal to n and greater than equal to 0. It may be 0 or greater than equal to 0. See, so next theorem. So next theorem, statement of theorem is that, see, this set close interval 0, 1. What is close interval 0, 1? It is set of all real numbers which lies between 0 and 1. So x less than equal to 1, greater than equal to 0 is uncountable. See, so we have to prove that this set that is close interval 0 1 is uncountable. So proof of this theorem. Again we will prove this theorem by contradiction. So on the contrary, assume that, suppose that, see, the set close interval 0 1 is countable. Suppose it is countable set. So naturally, if close interval 0 1 is countable, so there exists counting to the set. See, so hence we can write close interval 0 1 as x1, x2, x3, it goes to infinity. So there exists counting, means what is first element of close interval 0 and is x1, second element, third element. So you can give counting to elements of close interval 0 1. So here where every xi occurs in close interval 0 1. See, or you'll write, or every, see, every number in close interval 0 1 occurs as xi for some I. Means every real number in close interval 0 1 always lies in this set, means will be always in the form of xi for some I. So it is there. See, so expanding next, expanding each xi in decimal expansion. So we get what we get. We will write x1 in its decimal expansion. So here it is 0 point because all these x1, x2, x3 lies in close interval 0 1. So surely, and I'm not taking 1. I'm not taking 0. I'm taking numbers between 0 and 1. See, so exactly you know that first number is 0, last number is 1. So there is no problem of 0 and 1. See, surely I will write x1 as 0 point. I'm writing, see, a1 1. So suffix 1 and super suffix as 1 because it is first digit of x1. So second digit I'm writing a2 1. Similarly a3 1 and so on. So similarly we'll write second real number between 0 and 1 as 0 point. So what is decimal expansion of x2? So it will be a1 2, it will be a2 2, it will be a3 2 and so on. So similarly we'll write decimal expansion of x3. It will be 0 point a1 3, a2 3, a3 3 and so on. You can continue this process and you'll write decimal expansion of xn. So what is the decimal expansion of xn? So it will be 0 point a1n, a2n, a3n and so on. And you can continue this for all, see, numbers in close interval 0 1. So next, see, I'm forming a number. Let us see. I'm forming a number between close interval 0 1 in close interval 0 1, which is different from all these x's, but it is already element of this close interval 0 1. So next for that, see, let, so next I'm writing let b1 be, see, any integer from 0 to 8, from 0 to 8 such that, but how it is, such that b1 is not equal to a11. See, let next b2 be any integer from 0 to 8 such that, see, b2 is not equal to a22. In general, see, I can continue this process, means I'm taking b3 which is different from a33, b4 which is different from a44, and in general, let us see, in general, let, see, bn. So here in bracket I will write n varies from 1 to it goes to infinity, being any integer from 0 to 8 See, says that Bn is different from A and N. See, next. So let I'm taking y. It is 0.b1, b2, b3 up to bn, and it goes to infinity. See, so here you can observe. So first digit of y, that is b1, which is different from a11. So b1 is different from a11. So therefore, see, so y is different from x1. Second digit of y, that is b2, which is different from a22. So you can observe, see, so here b1 is different from a11, so therefore y is different from x1. b2 is different from a22, so therefore y is different from x2. Similarly, see, b3 is different from a33, and therefore y is different from x3. And similarly, see, so Bn is different from An, and therefore y is different from xn, and you can continue this process. So what you will get? So let y equal to, that is 0.b1, b2, b3 up to bn. See, so then what is the observation? So then for any n, the decimal expansion of y differs from the decimal expansion of xi's for I varies from 1 to it goes to infinity. See, because since you can write here bi is not equal to aii. See, hence also it is always true, decimal expansion of y is unique, means you can write y uniquely in its decimal expansion, because see, because no bn is equal to 9. So naturally what you are getting, see, hence, see, this y is not equal to xn for every n. See, hence y is different from xn, and y less than equal to 1 and greater than equal to 0, because what is y? It is point something. So naturally it lies between 0 and 1. So what I am getting? So I am getting one real number y which is different from xn, but it lies between 0 and 1, means I am getting, see, one real number in this set, that is close interval 0 1, but it is not here. So it is not in this set. So it is contradiction to, see, it is contradiction to close interval 0 1 is countable set, and its counting is this. So it's not possible. So what we get? Hence, see, this contradicts the assumption that every number in close interval 0 1 occurs among xj's or xi's. See, so this contradiction, hence close interval 0 1 is not countable. It should be uncountable. Is uncountable. So this is solution. This is proof of this theorem. That is closed interval 0 1 is always uncountable set. So next corollary to this theorem. Corollary. What is corollary? So next there is one corollary to this theorem. So what is corollary? Corollary. So corollary is that this set R of real numbers is uncountable. This set capital R, that is set of real numbers is uncountable. See, so proof is very simple. So how will prove this corollary? Suppose R is countable set. Suppose R is countable, then what happens? If R is countable, then every infinite subset of R should be countable. See, then every infinite subset of R is countable. Hence, see, closed interval 0 1 is countable. See, because closed interval 0 1 is a subset of R. So naturally closed interval 0 1 will be countable, but it is contradiction to previous theorem. See, which is contradiction to previous theorem, that what is previous theorem? Closed interval 0 1 is uncountable. See, hence our assumption is wrong. What is our assumptions? R is countable. So assumption is wrong, and therefore what should be true? Hence, see, R, that is the set of real numbers, is uncountable. So this is proof of this corollary, and which is straightforward. So in the same way, you can prove that set of irrational numbers is uncountable, and After that, we'll define algebraic number. So next, see there is one corollary. Next corollary, the set of irrational numbers is uncountable. See, so proof again, on the contrary, assume that, suppose that the set of the set, we can take q dash of irrational numbers is countable. See, suppose set of irrational numbers is countable set, so that is our assumption. So since q dash is countable, already we proved set of rational numbers is countable. Since we write, since q, the set of rational numbers is countable, and you write set of real numbers as q union q dash, that is rationals union irrationals, that is set of real numbers. Means you write set of real numbers as countable set union q dash, it is also countable, that is our assumption. Means you write real numbers as countable union countable, and it gives that real numbers will be countable. See, so what you will get, so it gives that set of real numbers, that is R, is countable. See, so which will be, which is contradiction to R is uncountable. Hence our assumption is wrong, that is set of irrational numbers is countable. Hence q dash, the set of irrational numbers is uncountable. So this is proof of this corollary, and we'll stop here. So in next lecture, that is lecture number 10. So we'll see algebraic numbers, then closed intervals and open intervals are equivalent sets. So there are some examples on equivalent sets in next lecture. So after that, in next, that is lecture number 11, we will see least upper bounds and supremums. So that will be end of the chapter, that is chapter number 2. So in lecture number 11, we will complete this chapter. In lecture number 12, we will start sequence of real numbers. So we'll stop here.